When I hit all of the non-square columns before, I glossed over some beautiful maths, and I want to return to that. I said before that there were some interesting diagonals, and while that's true, they really are amazing. I often see people trying to find primes by starting at say 7 and adding 6 repeatedly, which results in a bunch of prime numbers. 13, 19, 25 is not a prime, but 31, 37, 43 are. And while that's interesting, I think the quadratic progressions in this sort of visualization are far more interesting. They follow the same sort of pattern, but the numbers you add increase by 2 each step. If we look a bit more closely, we can see that each number is an odd number less than the number below it. The size of the odd number is determined by which row it's on. So the difference between the first row and the second row is 3, between the second row and the third row is 5, and so on. That means that a number on the second row, like 3, is 5 fewer than the number 8 below it, 4 fewer than the number 7 down and to the left, and 6 fewer than the number 9 that's down to the right. These progressions create some clear diagonals, and on some of them there are long runs of primes. Now they're certainly not uninterrupted, and you can see some obvious places where the square numbers break up the runs of prime numbers along the diagonals. There are some obvious diagonals that you're not going to find primes, so for example, all of the even numbers across every second diagonal. But when they happen, the diagonals continue fairly obviously. There are some diagonals that go down and to the right, and some that go down and to the left. In the smaller numbers, these runs aren't as obvious and they overlap with each other. So I'm going to skip ahead on the number line a bit and look at the gap between the original square numbers in the right-hand column, minus 9 squared and minus 10 squared. I'm going to start at 17 at the top of the 10th row. I'm going to follow the diagonal line down and to the left. I'm going to follow a simple rule. I'm going to add 20 the first time, and then 22, 24, 26, and so on. The first 15 of these numbers are primes. It's interrupted by the number 527, and then by the column of composites created by subtracting 10 squared. But the series continues after that, and enough that even at a distance you can pick out a clear line of mostly primes. In the same gap between 9 squared and 10 squared, there's another diagonal down to the right starting at 1, adding 22, 24, 26, and so on. That diagonal has 17 consecutive primes. In particular, I want to point to the number 233, which is the prime number at the intersection of these two diagonal runs of prime numbers in quadratic progression. While 233 isn't a twin prime, because of the way that the diagonals work, it's immediately below the twin primes 197 and 199, and above the twin primes 269 and 271. Above and below that are cousin primes, and above and below that are sexy primes. Now I think that's really cool, but an intersection number like 233 isn't particularly rare. If I zoom out a bit, you can really see clearly where these diagonals intersect, and in almost every case you'll find either twin primes or pairs of twin primes. Even where the intersection number isn't a prime number because of the square columns, the numbers above or below could still be twin primes. While ever these diagonal runs of primes exist, and it certainly doesn't look like they're rare, they'll intersect. And wherever they do, you'll definitely find twin primes, cousin primes, sexy primes, and in a lot of cases they'll even be in pairs. I think these diagonal runs of primes are also an interesting step into the conjecture that there's an infinite number of primes that are one greater than a square number. If you project along these solid diagonals, you'll find primes of this type. If we look to the right of the column of consecutive square numbers, we can see some amazing examples of quadratic progressions of primes. Notably, this diagonal here is generated by Euler's prime generating function k squared minus k plus 41, which has 40 odd consecutive primes. How awesome is that?